Okay, I'm going to be working through the Chapter 3 worksheet. This is under the Resources tab on the Sakai website. All right, so Chapter 3 is all about stereoisomerism and chirality. Stereoisomers are molecules that have the same molecular formula and the same connectivity, but they have different arrangements in space. All right, so these include enantiomers and diastereomers, and we'll go over the differences between those two. So chirality, a molecule is chiral if it has a non-superimposable mirror image. So if a molecule has a non-superimposable mirror image, if you look at the mirror image of a molecule and you can't twist it or rotate the bond for it to look like the first molecule, then the molecule is chiral. A chiral center is an atom with tetrahedral geometry. So again, we're dealing mainly with sp3 carbons right now, alkanes. So all of these carbons are going to have tetrahedral geometry. And what's special about chiral centers is that they have 4 different substituents attached to it. So a compound that's not chiral is called achiral. Okay. So let me give you an example of chirality with molecular model kits really quickly. So here we can see that we have two molecules and they're mirror images of each other, right? So a chiral molecule is something that you can't superimpose its mirror image. So if you take this as the first one and you try and superimpose this on this one, what you can do is twist the single bond and twist it around to a bunch of different conformations. So now you see you have the hydrogens lined up, but these 2 molecules are not lined up. You can twist it again, and now your red is lined up, but everything else isn't. And now we're back to the mirror image. So regardless of how you twist this single bond and rotate it, you're not going to get a superimposable mirror image, and that's what it means for a molecule to be chiral. So enantiomers are pairs of molecules that are mirror images of each other, basically what I just showed you with those model kits. They have chiral centers, and they share very similar physical properties. There's a significant difference, though, in that they polarize light in different directions. So 2 enantiomers, basically a general overview of what this means is that you can put a molecule inside some type of machine that's going to measure how much it polarizes a beam of light. And so in very general terms, you can think of it as one of these enantiomers that I just showed you would polarize the light, let's say 30 degrees to the positive or right direction. And the other one would polarize it 30 degrees, but to the left or negative direction. So these enantiomers are going to rotate the plane of polarized light by the same magnitude, but in different directions. So a solution containing only one of the 2 enantiomers is going to be called an optically active solution. So if you only put one of the enantiomers in, you would have, let's say you put in the one that rotated it to the positive direction, so you would get this rotation 30 degrees or whatever it is to one direction. So that would be an optically active solution. A racemic mixture is a 50-50 mixture of 2 enantiomers. So if you have the exact same amount of one enantiomer and the other, then you'll have a solution that is called a racemic mixture, and this is going to be optically inactive. So again, if you put both of them in, one of them polarized to the positive direction, one of them polarized to the negative direction, but in the same magnitude, what's going to happen is if you have 50-50 of these 2 enantiomers, they'll cancel out, and you won't get any optical rotation. So that's why this is called optically inactive. A compound that has no chiral center but is chiral due to restricted rotation is called an isomer. An example is biphenyls, and you can look those up. They're not often seen really in the first exam, but basically a reduction in bond rotation or restriction in bond rotation leads to them being considered chiral because you can't rotate the bonds even though they're single bonds to look like the other enantiomer. Okay, so now we're going to go to the second page. That was a lot of terminology, and we're going to get to some examples now. So enantiomers and nomenclature. Enantiomers are given either an R or an S configuration. So they're the same molecule, they have the same name, but they're given either an R or an S configuration. And this is how you go about deciding whether it's R or S. So you're going to assign priorities 1 through 4. And priorities have to do with how large or how significant the substituent is. So the example we're going to work with is going to be this. Okay, so this center carbon right here is going to be your chiral carbon because it has 4 different substituents on it. Okay, it has an aldehyde, it has an alcohol group, it has a methyl, and an ethyl. So there's 4 different substituents, so this will be your chiral carbon. So you're going to assign priorities for these substituents. So basically you want to start at the center carbon and you want to go out 1 atom from each thing. So here you would go to this first carbon. Here you'd go to the oxygen. Here you would go to the carbon, and here you would go to the carbon. And if you have atoms directly connected to the chiral center that are the same, you keep going until you find a difference. So here we have 1 oxygen and 3 carbons as our first atoms. So now oxygens are going to be more significant because they're larger than carbons. So you're going to give oxygen number 1. So the priority number for the oxygen would be number 1. Now we still have equivalent priorities for this, and this substituent because we're all at carbons at this point. So now the next thing that you go out to is going to be your next most significant atom. So you can think of this CH2CH3 as being a C with 2 H's attached to it, but this C is also connected to another C. So when you go out another step, so we all went out to this first carbon, and then you're going to go out another step. So from here, the most significant thing that this carbon is attached to after this is going to be this oxygen. The most significant thing that this carbon is attached to are these hydrogens because it just has 3 hydrogens on it. And the most significant thing that this carbon is attached to is this next carbon. So now we're looking at this carbon, this oxygen, and these hydrogens. So in order to make our distinction, we go in order from like the largest to the smallest. So we have an oxygen here, which is larger than this carbon. So we're going to give this a priority number 2. This carbon is better than having this hydrogen. So this is going to be given priority number 3. And this hydrogen is the lowest priority, so it's going to be given priority number 4. So we've numbered all of our substituents at this point. If you were to have a double bond or a triple bond, you treat it as being bonded to that atom twice or 3 times. So if you had a carbon double bonded to a carbon, then you would really consider that as being this carbon bonded to 2 carbons. So you can use that in your distinction as well. So let's say you had a carbon single bonded to a carbon and another substituent you had a carbon double bonded. Well, the carbon double bonded to the carbon would be better than the single bond because it's like it being attached to 2 carbons. Okay, so what you want to do now is make sure we're pretty much on step 4. So you want to make sure that you have the lowest priority group either pointing towards or away from you. Away from you is ideal, but pointing towards you is okay as well. And then you want to look and see whether you count these priorities clockwise or counterclockwise. So our lowest priority is on a dash, so that's going to be going away from us. So you can think of it as, let's say this is our lowest priority, and it's going to be going away from us. So you can think of it as looking at this like this, really like this, because it's going straight down. This oxygen, or this OH, is going to be coming out, and then this carbon is going to be going to the right. So now you want to count and see whether 1, 2, and 3 go in a clockwise direction or counterclockwise. So when you count 1, 2, and 3, we're going in this clockwise direction. So R is given the distinction when the 1, 2, and 3 go in a clockwise direction. So this is going to be an R enantiomer. If 1, 2, and 3 had been 1, 2, and 3, and it was counterclockwise, then we would have given it the distinction of S. Okay, so we're going to do some examples now. Okay, so I'd really like if you guys pause the video and work through these on your own, and then come and then start again once you're done. So what you're going to look at here is the first step. You want to assign these priorities. So you start at this chiral carbon here that has 4 different substituents on it. You have an alcohol group. You have a CH2OH group. So the C is attached to this C, and then the C is attached to the OH. This is a CHO group, which is an aldehyde. So sometimes they might be written like this, and you have to know that this is a carbon double bonded to an oxygen. And then this is a methyl group. So of these, when you move one out, we have carbon, oxygen, carbon, carbon. So our number 1 priority would be given to the oxygen. Okay, moving on from there, you want to move to the next atom that's attached. So basically, here we have hydrogen. Here we have a carbon that's double bonded to oxygen. So remember, when you have a double bond, it's like it's being bonded to that atom twice. Okay, so we have basically 2 oxygens here. On this carbon, we have the next thing out would just be hydrogens. And then here we have this carbon is bonded to 2 hydrogens, but it's also bonded to 1 oxygen. So we've already decided that this is number 1. The next thing we can decide is that this has an oxygen bonded to it, and this has an oxygen bonded to it. So these are going to be better than this one because it doesn't have any oxygens bonded to it. So that's definitely going to be your next lowest priority. So that's going to be your lowest priority. And now we're dealing with the in-betweens, in between the best and the worst. So here we have a carbon that's single bonded to an oxygen, also bonded to 2 hydrogens. Here we have a carbon that's bonded to a hydrogen, but it's double bonded to 1 oxygen. So if it's double bonded to an oxygen, again, it's like it being bonded twice to 2 oxygens, so that's going to outweigh this carbon. So this is going to be your next best, number 2. This is going to be your number 3 priority. Oh, I'm sorry, this should have been on a wedge. Okay, so now this is going to take a little bit of rotating, and I'm going to use the model kits to help us here. So what you want to imagine is that these two, since these two are in the same plane, we're going to make sure that when we show the model kit that these two are in the same plane as each other, okay? So if these are in the same plane, then you have this as this group coming out towards you, and then you have this as this group going backwards. So you have these two in the same plane, basically. I'm trying to make sure the camera can see it. This is coming out towards you, and this is going backwards. These aren't corresponding to what's actually on these substituents. It's just a way to look at them. So this is our lowest substituent, this one over here in the plane with this one. So we want this to be either coming out towards us or going backwards. I'm going to make it go backwards. So all you have to do is twist it so that this is going backwards. So if this moved to the back, then basically what we get now is these two in a plane and this one going up. So what you're going to end up getting, we can follow each like substituent along. So this is going to be our lowest priority. And then the CHO is what's going to be also in the plane with it. So when we turn it and look at this, we can see that the CHO is going down, okay? So we're going to draw the CHO going down. Okay. Again, if you look at it from the beginning, you have this group coming out at you. So the corresponding group that's coming out at you is going to be your CH2OH group. So again, when you rotate to look at this face and you have this group going down, your CH2OH group is going to be going to the left. And then one last time, when you have this red group going backwards, that's going to correspond to your OH, which is on the dash. So when you rotate to look at this face, you're going to have your red group going to the right. Just a little note about that, when it's written like that and your lowest priority is in the plane, sometimes there's different ways to do it. So I didn't have to rotate it like this. I could have rotated it like that. But the idea is that you want to look at this face of the molecule. You want to be looking at the interaction of these three substituents and then numbering them. And then looking and seeing whether it's clockwise or counterclockwise. So there's a variety of different ways I could have done it, and so you might not have done it exactly the same way, but what you should end up getting the same is whether you get a clockwise or counterclockwise conformation. So let's take a look at that. So our OH corresponded to our number 1 group, our CHO corresponded to our number 2 group, and our CH2OH is our number 3 group. So what direction do we get? We end up getting a clockwise direction. So this is going to be our R direction. All right. So our next example Okay, so where's our chiral carbon? That's the first thing to establish. Our chiral carbon is going to be this carbon right here, because this carbon has an oxygen attached to it. It has a carbon with all of this attached to it. It has this substituent, this carbon with 2 carbons attached to it, and it also has a hydrogen. So what's not showing is our hydrogen. And that has to be going into the paper because this one's coming out of the paper. So the first step is going to be to assign the priorities. So moving 1 out from this carbon, you have hydrogen, carbon, carbon, and oxygen. So the first thing you can do is assign our hydrogen the lowest priority. So our hydrogen is going to be our number 4, and it's in the plane. It's going into the paper right now. So it's going away from us, so we won't have to do any rotating on this example. Okay, so the next thing we can do is determine what's the best priority, if possible. So moving out, again, one atom, so you have oxygen, carbon, and carbon. So just moving out 1 atom, this oxygen is going to win over. So this is going to be our number 1 substituent. And again, now we just have to find number 2 and 3. So now we're at 1 atom out, so we're looking at this carbon and this carbon. This carbon's double bonded to oxygen, or to an oxygen, which is essentially like being bonded to 2 oxygens. And then we have this carbon that's bonded to a carbon, is also double bonded to a carbon. So it's like it's bonded to 3 carbons. But oxygen is better, so this is going to be our number 2. This is going to be our number 3. So our hydrogen's in the back, our lowest priority. So essentially what we can do is imagine that this looks like that and just say 1, 2, 3. So this is going to be an R conformation. Okay, another way you can see this is in a chair. So, and I'm going to tell you that we want to look at this carbon here. Okay? So this would also be a chiral carbon here. But we're going to look at this one. So what would be your first step? In my opinion, I would convert this to face. So you're going to convert it like this first, because it'd be easiest to see this way. So we talked about in chapter 2 that when you convert from face to chair, you have to decide whether you want your wedges to be up or your wedges to be down. I'm going to do that wedges are up and dashes are down. So if something is up on a chair, then it needs to be on a wedge in a face conformation. So this is going to be on this carbon, we're going to have the OH and it's going up. So I'm going to put it on a wedge on this carbon. Make sure you count your carbons. So 1, 2 carbons away, 1, 2. You're going to have this CH3 and it's going down. So when you convert this to face, it needs to be on a dash. Okay, so we're looking at this carbon again. So what is this attached to? This is attached to a carbon which has this kind of side of it. It has this carbon, and then it has this carbon. What else is it attached to? It also has a hydrogen. So that hydrogen's coming out towards us. Okay, so the first thing we can do is assign our lowest priority. So if you have a hydrogen and you don't have any other hydrogens, your hydrogen's always going to be your lowest priority. Okay? So what is our next, what can we do next? So if we move one atom out, we have 3 carbons. So moving one atom out doesn't distinguish best or the next best for us. Okay, so we need to move out again. So here, when we move out, we move to only hydrogens. Okay, when we move 1 from this carbon, you're going to be at another carbon. Okay, when you move 1 from this carbon, you're going to be at this carbon. Okay, so we know that this is the next worst one because it's only attached to hydrogens and not any more carbons. So this will be our number 3. Okay, but we can't distinguish yet between this carbon and this carbon. So let's move out again. So when you move from here, you're going to get to carbon. Okay, so we're at this point. When you move out 1 from this carbon, you're going to get to an oxygen. So now we have a distinguishing or differentiating point. So this oxygen is going to be better than this carbon. So this is going to be our number 1 priority. This is going to be our number 2 priority. I'm going to write it over here. So this side is our number 2. This side's our number 1. So we have 1, 2, 3, and 4. So this time 4 is coming out towards us, which is fine. You just have to remember that when it's coming out towards you, you have to look at the rotation and then reverse it. So let's look at that now. So this looks like it's going 1, 2, 3. That's going in a counterclockwise direction. Okay, so this looks like S, right? But the hydrogen is coming out towards us, and giving this R and S distinction is the rule is that your lowest priority has to be going away from you. So if it's coming towards you, you just have to reverse what it looks like. Okay? So it looks like S, but really it's R. All right. So we're going to move on to meso compounds. So a compound is meso if it has 2 or more chiral centers, but it has a plane of symmetry making it achiral, and if something is achiral, it's also optically inactive. Okay, so let's do some examples of this. And there's some tricks for determining whether or not this is a meso compound. All right, so this is going to be our example of a meso compound. So it has a plane of symmetry. We can pretty much all see that there's a plane of symmetry here, right? Okay, so you could fold that over, basically, or that's a mirror image right there. So one way to tell whether or not it's a meso compound is if there's a plane of symmetry and there's a configuration of RS. So what I mean by that is that one of the chiral centers has a configuration of R, and then once you go past this plane of symmetry, the configuration has switched. So let's look and see what the configuration is of this. So here we have this carbon, which is attached to a bromine and 2 carbons and a hydrogen. The hydrogen's going back, so we don't have to worry about it. Our bromine's going to be our best, so that's going to be number 1. Then you move out 1 carbon, and we're here, and we don't have any distinguishing factors yet. Then you have to move out again. So here we're at a carbon. This carbon's attached to a bromine, and this carbon is attached only to carbons and hydrogens. So this is going to be better. So it's going to be number 2. It's going to be number 3. And remember, our hydrogen is going backwards. That's number 4. So 1, 2, 3 goes in a clockwise direction. So this is going to be R. Okay, let's look at this chiral center. So now we have a bromine, which is going to be number 1. And again, it's the same, it's a plane of symmetry. So we know that this substituent's going to be better because it has the carbon that's attached to the bromine. This substituent's going to be lower, so number 3. And hydrogen's going to be the lowest. So now we have 1, 2, 3. This is going in a counterclockwise direction. So S. Okay? So this is a meso compound because you have a plane of symmetry and you also have a configuration of RS across the plane of symmetry. So if your chiral centers switch conformation, then you have a plane of symmetry, and you probably have a meso compound. Okay, so let's look at this. So the plane of symmetry in this one is going to be right here. Okay, so Br is going to be our number 1 substituent. Hydrogen's going to be going back, so we don't have to worry about it. This carbon that's attached to the bromine is going to be better than this carbon that's attached only to hydrogens. So we're going to have 2, 3, and hydrogen is 4. So 1, 2, 3, that's going counterclockwise. So we have S here. And then over here we have bromine. It's going to be number 1. This carbon attached to the bromine is going to be better than this carbon attached only to hydrogens. Okay, so we have 1, 2, 3. That's going clockwise, so that's going to be R. Okay, so again, we have a plane of symmetry, and then we have chiral centers going from R to S. So we have a meso compound. All right. So these might seem pretty evident, but sometimes you'll get something like this. Okay, so you might get something like that. Now, these are conformers, this and this right here. Single bonds can rotate. So basically, if you rotate this bond, you can get this structure right here. Okay, so you have to be careful, pay attention. to whether or not the bond can rotate and lead to a meso compound. So the internal plane of symmetry might not be so obvious here, but if you were to rotate it and make it look like this, you would have seen the plane of symmetry. Again, you can check the conformations on this. This is going to be R, and this is going to be S. Okay? All right, so diastereomers. Diastereomers are stereoisomers that do not relate through mirrors. Example is cis and trans. So this versus this. And these are diastereomers, but be careful because they have to have a double bond or be part of a ring to be cis or trans. So don't get fooled because sometimes they might ask you if something is cis or trans, but if it's not part of a ring or a double bond, then it's not going to be cis or trans. Okay, so another example, diastereomers. Okay, so let's look at whether or not these are diastereomers. So, basically, if it's an enantiomer, every chiral center will switch configuration between R and S when you go over the mirror. So this is a mirror image of it. It's just that the mirror image has been flipped over. So it is a mirror image, though. So what you want to look at and see whether this is an enantiomer or a diastereomer. So you can do the configurations for each of these if you'd like, or you can see that this switched and went from being on a dash to being on a wedge. So let's do the configuration for these two. So this is going to be your number 1 priority on this carbon here. We're looking at this carbon. This is going to be your number 2 priority because these substituents are closer. This is going to be your number 3 priority because it's only attached to carbons up until here. And your hydrogen is going to be coming towards you. So if the hydrogen's coming towards you and it looks like it's going in a clockwise direction, so it looks like R, but hydrogen's coming towards you, then you know it's really S. Okay, so let's look at it here. This is going to be number 1, like we said. This is going to be number 2. This is going to be number 3. So, but this time the hydrogen's going back into the page. So the wedge is coming out, this chlorine. So this is 1, 2, 3. This is going in a clockwise direction, so it looks like R, and the hydrogen is going back, so it is R. Okay? So this center changes from S to R. You guys can go ahead and do the conformations for this carbon and this carbon, but they will switch from here to here, okay? So just like it did from this one went from a dash to a wedge and it switched conformation, these will also switch conformations. So since everything switches conformation, the relationship between these two is that they're enantiomers, mirror images. Okay. So because the stereochemistry reversed for each of these, then they are mirror images of each other for each chiral center. Now let's look at okay, so here, this is the same as over here. So we know this goes from S to R, okay? Now let's do the examples for this one. So this chlorine is going to be number 1. This is going to be number 2 because this carbon's attached to a bromine, whereas if you go 1 out, this carbon is only attached to another carbon. So this is going to be number 2. That's going to be number 3. Okay, and your hydrogen is going into the page. So you have 1, 2, 3 going in a clockwise direction. So this is going to be R. Now, when you move over to this one, you have the chlorine, which is still number 1. You have this carbon, which is still number 2. Okay, and you have this carbon, which is still number 3. So this is going to still be, goes in a clockwise direction, still going to be R. Okay, what about this bromine? So this bromine, this gets kind of messy because there's not enough space. So this bromine's number 1. Okay, this carbon's going to be number 2. And this carbon's going to be number 3. So this is going in a counterclockwise direction, and your bromine is coming out on a wedge. So since the hydrogen, the 4th priority, is going backwards, then you know that it is what it looks like. So it looks like S, and it really is S. Okay, what about over here? This bromine's going back, so that's the first thing. The hydrogen's coming towards us, so we know that we have to reverse whatever it ends up looking like. Bromine's going to be number 1. This carbon's going to be number 2. This carbon's going to be number 3. So you have looks like S, but the hydrogen's coming forward, so it's really R. So now let's compare. This carbon, or this chiral center here went from S to R. Okay, so that's what it should do for an enantiomer. This carbon here went from S to R. Okay, and what about this carbon here? So this carbon went from R to R. Okay, so since not all of the chiral centers reverse their stereochemistry, the relationship between these two is that they're diastereomers. So in order for them to be enantiomers, if you have more than one chiral center, then everything has to reverse its stereochemistry, all of the chiral centers, in order for them to be enantiomers. If they're diastereomers, you might have one or more groups that does not reverse its stereochemistry. Okay. So Fisher projections are basically, I'm going to do a quick overview of this. You're going to see them looking like this, and what they really are, I don't think any of the professors are going to get to this before exam 1. So you have your bow ties. And then those. So what this really is if you were to build a molecule and make it look like this, that's how you draw it in a Fisher projection. So if you have a low priority on the horizontal, that's not really helpful, because if you have a low priority on horizontal, let's say your hydrogen was, here or here or here or here, then you would have to rotate this in order to figure out the stereochemistry, whether it's an R or S. So if you have your hydrogen here or here, then it's very easy to just say 1, 2, 3 or 1, 2, 3 and figure out whether it's R or S, because your lowest priority is going backwards already. Okay?